There is something in deep space that genuinely challenges the limits of human comprehension, not because the concept is abstract or the mathematics is complicated, but simply because the scale involved is so far removed from anything we have ever experienced that our minds keep trying to shrink it down to something manageable and failing. More than 1 billion light-years from where you are sitting right now, at the gravitational heart of an enormous galaxy cluster, there exists a structure so vast that calling it a galaxy almost feels inadequate. Its name is IC 1101, and by the time you finish hearing its story, the universe will feel both larger and stranger than it did before. But to arrive there, we need to make a journey, not a physical one, but a mental one, a gradual stretching of perspective that begins here, with you, on this small, rocky world, and moves outward step by step until the distances involved stop feeling like numbers and start feeling like something real. Because the biggest mistake we can make when approaching a subject like this is to skip ahead to the biggest number. Size without context is just a statistic. What we want is understanding. And understanding requires us to build our sense of scale from the ground up. So let's begin. The ladder of scale. You live on Earth. That might sound obvious, but it is the right place to start, because Earth is the scale we know. It is the scale our senses were built for. A mountain takes days to climb. An ocean takes weeks to cross by ship. The whole circumference of the planet, roughly 40,000 kilometers, is a number most people have memorized, and it still feels impossibly large whenever you try to picture walking it. And yet the moment you step off Earth and look at the solar system, that number stops mattering. Consider Jupiter. When you place Earth beside the largest planet in our solar system, our world becomes something close to a marble set beside a basketball. Jupiter is so wide that more than 1,300 Earths could fit inside its volume. Some of its storms are wider than our planet's entire diameter. The famous storm known as the Great Red Spot has been spinning for centuries, and for much of that time it was large enough to contain Earth entirely within its swirling edges. Earth, that enormous world holding all of human history, fits inside a single storm on another planet. And yet Jupiter, for all its size, is still just a planet. It does not produce its own energy through nuclear fusion. It does not shine with its own light. It reflects light borrowed from the sun. So let us look at the sun. The star at the center of our solar system contains about 99.8% of all the mass in the solar system. Every planet, every moon, every asteroid, every comet, all of it together accounts for only the remaining 0.2%. The sun's diameter is about 1.4 million kilometers. More than 1 million Earths could fit inside it. From Earth, it blazes so intensely that you cannot look at it directly. From the perspective of the solar system, it is everything. From the perspective of the galaxy, it is one ordinary star among hundreds of billions. There are somewhere between 100 and 400 billion stars in the Milky Way alone. Some are dozens of times more massive than our sun. Some are thousands of times brighter. Our sun is a fairly average middle-aged star sitting in a relatively quiet stretch of a spiral arm about 26,000 light-years from the galactic center. It is one grain in a vast field of fires, each separated from its neighbors by distances that take years to cross even at the speed of light. Let that sink in. Light, the fastest thing in the known universe, capable of circling Earth more than 7 times in a single second, takes more than 4 years to travel from our sun to the nearest neighboring star. 4 years of travel at 300,000 kilometers per second, and you have only reached the closest neighbor. The Milky Way itself stretches about 100,000 light-years from edge to edge. A beam of light crossing our galaxy from one side to the other would need 100,000 years to complete that journey. During that time, civilizations could rise and collapse. Species could evolve and vanish. The entire span of recorded human history could play out dozens of times over. This is what a galaxy truly is. Not a pretty spiral in a textbook, not a smear of light on a photograph. It is a structure so immense that even light needs 100 millennia to traverse it. And our galaxy, the Milky Way, is not especially large by galactic standards. Beyond the Milky Way. For most of human history, the Milky Way was everything. When people looked at the night sky and saw that faint pale band stretching overhead, they had no idea what they were really looking at. Eventually, as telescopes improved, astronomers came to understand that the Milky Way was a galaxy, a vast rotating disk of stars held together by gravity, and beyond its edges appeared to lie only darkness. But scattered through that darkness were faint, blurry patches. They were called nebulae, from the Latin word for clouds. Some were exactly that. Clouds of gas and dust belonging to our own galaxy. But others were something far more profound. They did not belong to the Milky Way at all. When astronomers finally determined the distances to some of these patches in the early 20th century, the result upended everything. They were not nearby clouds. They were entire other galaxies. Separate island universes, each containing billions of stars, lying millions or even hundreds of millions of light years away. What looked like a smudge through a telescope eyepiece was actually a structure comparable to the Milky Way in size and complexity, so impossibly far away that billions of individual stars blurred together into a faint haze. This discovery changed our understanding of the cosmos completely. The Milky Way stopped being the universe and became just one galaxy among many, not among a few, among hundreds of billions. Galaxies come in many shapes and sizes. Some are small, irregular systems with only a few billion stars, dwarf galaxies. Some are large, graceful spirals like the Milky Way or Andromeda, with arms curving around bright central regions. Others are entirely different in character. Massive, smooth, roughly oval-shaped systems called elliptical galaxies. These tend to be larger than spirals on average, and the very biggest galaxies in the observable universe are almost always of this type. Giant ellipticals, grown enormous through a very particular kind of history. To understand why, you need to understand what happens when galaxies meet. How giant galaxies grow. Galaxies do not sit still. They move through space, drawn by the gravity of their neighbors, their clusters, and the vast invisible framework of dark matter that underlies the structure of the cosmos. When two galaxies come close enough, gravity takes charge, and what follows looks nothing like any collision we might picture from everyday experience. Stars within galaxies are separated by such enormous distances that when two galaxies interact, individual stars almost never physically strike each other. The violence is not in direct impact. It is in the gravity, reaching across the entire encounter, tugging on billions of stars simultaneously, bending orbits, stretching paths, pulling long tails of starlight outward into the surrounding space. When two spiral galaxies interact, the consequences unfold over hundreds of millions of years. Their arms get warped and distorted. Enormous streams of stars are drawn out like ribbons of light. Gas clouds are compressed, often triggering waves of rapid star formation. The two galaxies circle each other, separate, then slow down and fall back together again, bound by their mutual gravity. With each pass, more of their original structure is scrambled. Eventually, the two separate identities dissolve into one. The resulting object no longer resembles a pair of spirals. It looks like a single, smoother, rounder structure, an elliptical galaxy. This process, repeated over billions of years, is one of the primary ways the universe builds its largest objects. A galaxy sitting at the center of a rich cluster is in the ideal position for this kind of accumulation. As other galaxies drift under the influence of gravity, some approach closely enough to interact. Some have their outer stars gradually stripped away. Some merge directly with the central giant. Over cosmic time, the central galaxy collects mass from all of these encounters, growing heavier, larger, and more dominant. This process is sometimes called galactic cannibalism, though the phrase makes it sound faster and more dramatic than it actually is. In reality, it is slow, patient, and almost geological. Think of how a river delta accumulates, not through any single flood, but grain by grain over millions of years. A central galaxy grows the same way, one ancient encounter at a time, each one adding a little more mass and leaving a little more history. This growth leaves marks. The outer regions of a giant elliptical galaxy often contain stars that were not born there. They originated in smaller galaxies that no longer exist as separate systems. Their original hosts were pulled apart by tidal forces, stripped of their stars, and consumed, but the stars themselves survived. They became part of a vast, faint outer cloud, a stellar halo, surrounding the central galaxy. That halo is diffuse and dim, but it is evidence. It is the cumulative record of every system the galaxy has absorbed. This is also why giant elliptical galaxies look the way they do. They have no spiral arms because repeated mergers disrupted the organized rotation that creates those structures. Their stars orbit in many directions, giving the galaxy a smooth, cloud-like appearance rather than a flat disk. Their outer envelopes fade gradually, rather than ending sharply, dissolving into surrounding space like a city whose suburbs trail off imperceptibly into countryside. IC 1101, a faint blur with a big secret. On the evening of June 19, 1790, the astronomer William Herschel swept his telescope across the sky and noted a faint, soft patch of light in the constellation Virgo. He had no way of knowing what he was really seeing. To him, it was just another blur, one more entry in a growing catalog of mysterious objects, something to record and move on from. What he was actually observing was a galaxy more than 1 billion light-years from Earth. The photons entering his telescope that night had begun their journey before our solar system formed. They had been traveling through expanding space for longer than complex life had existed on Earth by the time they reached his eyepiece. He was seeing the deep past without knowing it. That faint smear would eventually be cataloged as IC 1101. For decades, it remained unremarkable among thousands of similar objects distributed across the sky. It was only as telescopes grew more powerful and astronomers developed better tools for measuring distances and analyzing starlight that the true nature of IC 1101 came into focus. It was not just any galaxy. It was the dominant central galaxy of a massive structure called Able 2029. A rich galaxy cluster roughly 1.07 billion light-years from Earth, and it was immense. The size problem. Describing the size of IC 1101 is more complicated than it might appear, and being precise about it actually makes the galaxy more interesting. The most extreme figures you will encounter suggest IC 1101 stretches across 6 million light-years, 60 times the diameter of the Milky Way. That number comes from tracing the very outermost extensions of the galaxy's halo, where IC 1101 gradually dissolves into the surrounding cluster. It is a real measurement, but calling it the galaxy's size is a bit like measuring a city by its most distant rural outpost, rather than where the actual urban landscape ends. The bright concentrated body of IC 1101 is considerably smaller. But even by conservative measurements, IC 1101 remains one of the largest galaxies identified in the observable universe. Its total stellar mass is extraordinary, where the Milky Way contains between 100 billion and 400 billion stars. IC 1101 may harbor 100 trillion or more, potentially hundreds of times as many as our own galaxy. The difficulty of measuring IC 1101 reflects something genuine about the nature of giant elliptical galaxies. They have no sharp edge. Brightness decreases gradually until the galaxy's glow can no longer be distinguished from the background light of the surrounding cluster, a diffuse shimmer from stars that were long ago stripped from their home galaxies and now drift freely through the cluster without belonging to any particular system. Think of IC 1101 not as an object with a defined boundary, but as a continent of stars whose coastlines dissolve into the ocean of the cluster rather than meeting a clear shore. The hollow heart. One of the most striking features of IC 1101 is not found in its outer regions. It is found at its center, or rather in what is missing there. Most galaxies show an increasing density of stars as you move from their outskirts toward the core. IC 1101 deviates sharply from this pattern. Its central region is significantly less bright and less dense in stars than the surrounding galaxy would predict. Something has removed stars from the heart of this galaxy, leaving a vast depleted region at the center of one of the largest structures we know. The explanation involves supermassive black holes and galactic mergers. Every large galaxy is believed to contain a supermassive black hole at its center. When two large galaxies merge, each brings its central black hole into the new combined system. The two black holes do not immediately merge. Instead, they form a binary pair, orbiting each other and slowly spiraling closer over millions of years. As this binary tightens, stars that pass too close are flung outward at high velocity through a gravitational slingshot effect. Over time, and especially after multiple mergers, this repeated ejection can excavate a large, star-depleted cavity at the galaxy's center. In IC 1101, the depleted core is enormous, consistent with a galaxy that has experienced not just one major merger, but many across its history. Each merger brought a new supermassive black hole. Each new binary pair ejected more stars. The center grew more hollow, even as the galaxy itself grew larger. This creates one of the most striking paradoxes in the story of IC 1101. The galaxy grows and hollows at the same time. Stars accumulate in its outer halo through mergers and tidal stripping. Stars are expelled from its center through black hole dynamics. The galaxy becomes simultaneously more massive and more empty at its heart. The largest galaxy we know carries its most dramatic evidence of destruction right at the point that should be its brightest center, the ultramassive black hole. Given the vast scale of IC 1101 and the enormous depleted core at its heart, the black hole, or accumulated product of multiple merged black holes, at its center is likely among the most massive objects we know of. Our Milky Way's central black hole, Sagittarius A star, mass is about 4 million times the mass of the Sun. That is genuinely extraordinary by human standards, but in the broader context of large galaxies, it is actually on the modest side. In IC 1101, the central black hole is estimated to fall into the category astronomers call ultramassive, possibly massing tens of billions of times the mass of the Sun. A black hole of that scale has an event horizon, the boundary of no return, that stretches across a region that would dwarf our entire solar system many times over. The event horizon is not a physical surface. It is a boundary in space-time, the point at which the curvature of space becomes so extreme that no path leads outward. Cross it in any direction and you cannot escape. Not matter, not energy, not light. From the perspective of the galaxy, however, what matters most is what happens just outside the event horizon. As gas and matter fall toward the black hole, they can be heated to extreme temperatures and drive powerful jets of energetic material outward into the galaxy and beyond. These jets, moving at significant fractions of the speed of light, extend hundreds of thousands of light years from the center, pushing into the hot gas filling the surrounding cluster and heating it so thoroughly that it struggles to cool down and form new stars. This creates a feedback loop shaping the galaxy's entire long-term evolution. The galaxy feeds the black hole. The black hole regulates the galaxy's future. This shifting equilibrium, each influencing the other across billions of years, is one of the deepest relationships in modern astronomy, and it is one of the reasons IC 1101 no longer forms large numbers of new stars. It now shines mainly with the warm reddish light of aging stellar populations, the glow of stars born during more active periods in its history. The cluster that fed the giant IC 1101 lives within Abell 2029, and that location is not a minor detail. It is fundamental to why the galaxy became so large. A galaxy cluster is one of the largest gravitationally bound structures in the universe. It may contain hundreds or thousands of galaxies, all moving within a shared gravitational framework. But the galaxies themselves are actually the smallest component by mass. Most of the ordinary matter is not in the stars. It is in a vast cloud of extremely hot gas called the intracluster medium, which fills the spaces between galaxies and radiates in X-rays. Surrounding all of this, accounting for the majority of the cluster's total mass, is dark matter. Invisible material that reveals itself only through its gravitational effects. Together, this creates an enormous gravitational well. Over billions of years, galaxies drift inward, slow down through gravitational interactions, and eventually sink toward the cluster core. IC 1101 sits at the deepest point of that well, in the most privileged position for accumulating material delivered by gravity from the surrounding environment. Think of it as cosmic sedimentation. In a body of water, particles settle toward the bottom over time. In a galaxy cluster, stars and stripped galactic remnants slowly accumulate toward the center. IC 1101 has been sitting at that bottom, collecting what the cluster delivers, for billions of years. This is why IC 1101 cannot be fully understood in isolation. The galaxy did not grow large in a vacuum. Its size is as much a product of its environment as of its own internal history. A galaxy with a similar starting point, born in a quiet and uncrowded region of the universe, would never have grown anything like this large. It would not have had enough material falling its way. This is one of the deeper lessons of IC 1101. In the universe, location shapes destiny. Galaxies born near the centers of massive clusters develop very different futures from those born in sparse, isolated regions. Environment is not a secondary factor. It is one of the primary drivers of how structures evolve over cosmic time. The cosmic web zoom out further still, and galaxy clusters themselves are not isolated islands. They are nodes in an even larger structure, what cosmologists call the cosmic web. On the grandest scales, matter in the universe is not spread uniformly. It is organized into an intricate network of filaments, enormous threads of galaxies and gas stretching hundreds of millions of light years, with vast, nearly empty voids between them. Where these filaments intersect, matter concentrates into galaxy clusters. The cluster nodes in this web are the densest, most gravitationally intense regions in the observable universe. This structure grew from the very beginning of everything. In the first moments after the Big Bang, the universe was almost perfectly uniform, but not quite. Tiny fluctuations in density existed at the quantum level. Over hundreds of millions of years, gravity amplified these differences. Slightly denser regions attracted surrounding matter. Gas collapsed, stars ignited, galaxies formed. Those galaxies gathered into clusters along the intersections of matter filaments. Able 2029 is one knot in that web. IC 1101 is the dominant galaxy within that knot. Its story connects through an unbroken chain of cause and effect all the way back to the earliest moments of cosmic time. What time will do scale can tempt us into imagining permanence. When we hear that a galaxy contains 100 trillion stars and spans millions of light years, it feels natural to assume that nothing could diminish it. But the universe does not spare its largest creations from the passage of time. It simply takes longer to transform them. IC 1101 is not forming large numbers of new stars today. The supply of cold, dense gas needed for star formation has largely been exhausted, heated, or stabilized by energy from the central black hole. What remains is a vast population of aging stars, slowly burning through their remaining fuel. On timescales of trillions of years, those stars will age and dim, generation by generation, until the galaxy grows progressively darker. This will not happen suddenly. There will be no dramatic explosion. The galaxy will simply grow quieter over time, as its remaining fires burn lower and eventually go out. The universe itself is also changing. The expansion of space, accelerating under the influence of what we call dark energy, is gradually separating distant regions from one another. Galaxies beyond the local cluster will continue to recede. Their light will be stretched toward longer wavelengths until eventually distant objects slip beyond the cosmic horizon, the boundary beyond which the universe is expanding faster than light can travel to bridge the gap. In the far future, a hypothetical observer within IC 1101 would look out at a much emptier cosmos. The great filamentary web we can map today would be invisible, its most distant parts having retreated beyond reach. The universe would not have become smaller. It would have become profoundly lonelier. This makes our current era worth appreciating. We live at a time when the universe is still bright enough to be studied. Ancient light from objects more than 1 billion light-years away still reaches our instruments. When we observe IC 1101, we are not only looking at a place, we are looking at a preserved moment in cosmic history, delivered across an ocean of expanding space by light that began its journey before our planet formed. The scale that humbles and connects. There is a specific feeling that comes from fully engaging with what IC 1101 truly is. It begins with being made to feel small, and rightly so. The galaxy contains potentially hundreds of times as many stars as the Milky Way. Its outer halo stretches across distances that take light millions of years to cross. Embedded within it are the remnants of smaller galaxies that no longer exist as separate objects. Entire systems containing billions of stars now dissolved into the outskirts of something larger. Against that backdrop, our sun is one of 100 trillion stars. Our solar system is an invisible point. Our planet is beneath the threshold of detection, and you, with all the complexity of your experience, are a temporary arrangement of atoms assembled on a small world, capable of knowing that IC 1101 exists. But here's the other side of that feeling. The atoms in your body were forged in stellar interiors. The oxygen you breathe was scattered by ancient supernovae. The same gravity that assembled IC 1101 across 1 billion years of mergers also holds you to the ground beneath your feet. You are not separate from the universe that built that giant. You are a part of it. And there is this. The universe built something large enough to stagger the imagination, and then, on a small rocky planet orbiting one ordinary star in one typical galaxy, it assembled something capable of imagining the thing that staggers it. IC 1101 is a record of cosmic history written in starlight. Its halo tells of galaxies consumed. Its smooth, rounded shape tells of mergers that erased older and more delicate structures. Its hollowed core tells of black holes working in the dark, flinging stars outward as they spiraled closer. Its position at the center of observable 2029 tells of the profound importance of environment and gravity. And its sheer scale tells of what the universe can accomplish when it has enough matter, enough time, and enough of the patient force that draws everything together. We see it not as it is today, but as it was, a glimpse of the deep past delivered across more than 1 billion light-years of expanding space. Whatever IC 1101 looks like right now will not be known to us for another 1 billion years. By the time that light arrives, everything we know will have transformed beyond recognition. But right now, in this present moment, we can look at a point of faint light in the sky and understand that behind it lies an empire of stars, assembled slowly from the ruins of countless smaller galaxies, shaped by the invisible hand of dark matter, governed at its heart by one of the most massive black holes we know of, glowing quietly at the bottom of a gravitational well at the center of a massive cluster. That is what the biggest galaxy looks like. Not a number, not a record. A story built from gravity and time, written in light and read from a small world by minds that have only recently learned to look.